Okay, welcome to screencast number one on electric potential, energy, and power. First, a quick review. The electric potential at a given location in a circuit is the amount of energy per charge at that location. The location of the highest potential in any of our DC circuits is going to be at the negative terminal. At that point, the electrons will have the most energy. As charge moves through the external circuit from the negative to the positive, it's always going to flow from negative, high potential, to positive, low potential terminal. The charge loses potential energy. As charge moves through the battery, it gains potential energy. The difference in electric potential between any two locations within the circuit is known as the electric potential difference. It's sometimes called a voltage. Now, that's not a very descriptive word. It's a person's name, Alessandro Volta. So it is a common usage, but not very descriptive. Potential difference definitely describes more what is going on. Since it's measured in volts, the symbol will be V, and then our symbol for change is delta. So delta V is the potential difference between 2 points. V is essentially the potential at any given single point. The rate at which charge moves past any point along the circuit is known as the current. It is a rate, so it would be expressed in the unit the ampere. And since it's a rate, 1 ampere is equal to 1 coulomb of charge passing a space in 1 second of time. So anytime you see a rate quantity, you're just going to divide by time. Okay, back to the electrical potential diagrams. We went over these the last time, but this is a very useful tool for expressing what's going on within the circuit. So we have 6 labeled points. We're going to place the potential at those points on the diagram, and we're going to track the potential as we move around. Okay, now I'm going to start at the negative terminal of the battery. That's where the electron has the most most energy. So it has the highest potential. So up here, I'm going to mark point A. Now, as we travel around the circuit from negative to positive, in wires, we assume there's very little energy loss. So we assume that our wires have no potential difference. So from A to B, we would stay at the same point in terms of the height of our energy level. Now, as we pass across the light bulb from B to C, we're going to get a drop. Now, we call it a drop because it's similar to a ball falling from a height. You can tell that we're going to lose energy because the light bulb glows. That's going to indicate energy is being given off to the surroundings. The only way it could be given off is if it came from something, in this case, the electron, the charge. Now again, C to D, we're talking about moving across a wire. We're going to assume, that's point C, we're going to assume that it doesn't change its potential any in that section. So that's just a flat line across. Now we are at a lower potential than we were when we came out of the battery at point D, but we are not finished yet, so we fight our way, our charge fights its way across from D to E. Now once it's gotten to point E, there's nothing in its way between there and the positive terminal. Now the positive terminal is going to be 0 charge. So once we have gone from point D across to point E, we will have reached 0 charge. Once we reach zero potential. Once we reach 0 potential, there's no place to go except back to the positive terminal of the battery. Now the battery can provide energy to our electrons again and then send them around the circuit. Okay, so now notice this one, they have A at the negative. I'm going to actually therefore start at that same point that we had before. So here's our start point. A, again, the negative terminal of the battery is where we have the highest potential. No change between there and the wire B. Now this time there are 1, 2, 3 places where we can lose the energy. Now in our first diagram, I dropped about halfway because we had 2 objects that could use the energy. In this case, between B and C, I'm going to drop about a third of the way. And we go from C to D, no change. Now another third drops us to point E, over to F, no change. Then we're going to drop the rest of the way to the bottom where we have no potential left at all, which is H. So here at G, we will have fallen back to 0. Okay, now in both of these drawings, I have assumed that the resistance of all the light bulbs is the same. They're the same basic size. If one's bigger than another, then we'll see a bigger drop at those. So larger resistors or resistances will use more of our energy. Okay, so let's take one more path around a circuit. This is all three of these circuits have been series circuits. There's one object after another, and we're going to compare the potential. So again, here at point E, that must be our highest potential. This is a 24 volt potential difference. So the delta V of the battery is 24 volts. So if we start with 0 here, which is what we always have at the positive terminal, the battery will put in 24 volts. That's 24 joules for every coulomb of charge. And therefore we will have a potential at point E of 24 volts. Now as we go through the first ammeter, we see that we've got 2 amps flowing through the wire. A good ammeter, a perfect ammeter, would have a resistance of 0, so there will be no potential difference across an ammeter. We're going to assume that they are high quality meters. Now as we go through this light bulb, we're going to lose a certain amount of our potential. We will have a potential difference. From Ohm's law, that delta V is equal to I times R, and I is current, R is resistance. So we have a current of 2 amperes times 6 ohms, so we will have a delta V, a potential difference of 12 volts. Now that means this time it's not an energy source, so we're going to lose 12 volts. So by the time we get to point D, we're going to have taken away 12 volts from 24, so 24 minus 12 is 12 volts. Now between these 2 points, there's nothing to use up the energy, so we're going to have the same energy and therefore the same potential between these 2 points, so that's still going to be 12 volts. Now if I know the current in a series circuit, I know the current everywhere in a series circuit. It all has to be the same. There's only one path. So the delta V at this particular light bulb is again going to be I times R, but we're going to use the resistance of that light bulb. So it's 2 times 2, that's 4 volts. And again, we're losing the potential. So by the time we get to point B, we started out here with 12. We've lost 4 in the transition across this light bulb, so that means we're down to 8 volts of potential. Now in this one, again, delta V is I times R, and we have 2 times 4, and that's going to be a delta V of 8 volts. Now 8 minus 8 gives us a potential, and we should have been able to say this from the beginning, of 0 volts. Once we have gone through all the items in a circuit loop, we must have used up all of the potential that we had at the beginning, because the positive terminal of the battery is going to be 0. So we started with 24. If I add up all those individual changes in potential, I need to get back to 24. So 12 plus 4 is 16, plus 8 is 24. So we put in 24, we used up 24. That will always be true in basic DC circuits. Okay, next time we'll look a little bit at calculating power and using the rate at which we change the energy in our circuits.